Hi there, and welcome to Kung Fu Physics, where we are working our way through the practice physics GRE problems. Today's problem is going to be off the 1986 practice exam, and it's number 37. So dig that one out. 1986 test, number 37, looks something like this. This is a classical mechanics problem. It's one of the easier problems, I would say. There are two very solid approaches to doing this problem that I would say are both pretty quick, actually. So we're going to do the tricky way, sort of. The tricky way first, and then we'll go into the, I guess, more obvious way. Again, in these problems, I tend to scan the answers first. So I would scan the answers, and when I looked at these answers, what I'm looking for is differences. Are there some things that are not present in some of the answers that are present in the other ones? Right off the bat, I'm not seeing the omega in the first two. That's of interest to me. The other thing is looking at D and E are of interest to me because they are very, very similar, but one of them has an omega squared and one has an omega to the fourth. That's interesting to me because I know the units are going to be different on that, and that's actually promising for helping me to eliminate answers. So I would dive into this problem, number 37. The figure above represents a point mass M attached to the ceiling by a cord of fixed length L. If the point mass moves in a horizontal circle of radius r with uniform angular velocity omega, the tension in the cord is. So I'm looking for a force. After a quick read through, I realize I'm looking for a force. I can do look for dimensions on the answers to see if they're a force. A and B both are forces because r over L is dimensionless, cosine of an angle is dimensionless, but mass times an acceleration is a force. They're okay dimensionally speaking. C is not a force. The denominator there, the sine of an angle, is dimensionless, but then I have m omega r. M has dimensions of, M would have units of kilograms, omega would have units of inverse seconds, and r would have units of length, of meters. So I would get something like kilogram meters per second rather than kilogram meters per second squared. Clearly, that's wrong. Right off the bat, if I am looking for a force and I see an answer like C, I can X it out. As it turns out, the same thing goes for D, because if I look very carefully at those units, you are trying to add two things under a square root sign, you'll notice. And you're trying to add an acceleration squared to something that's not an acceleration squared, because omega times r would not have units of acceleration. That would have units of a velocity, because again, you've got kilograms per meter, for example. And so that's wrong. Right off the bat, C and D are wrong by having the incorrect units. I could X them out and be confident, a little more confident in this problem, because I'm only looking at 3 remaining answers. I can actually knock out 2 more of the answers by thinking conceptually, which is not a bad thing to do. It's great to be mathematical and rigorous and a rocket scientist and do it all, but there's nothing wrong with thinking things through in your head and getting a physical situation. In fact, it's very useful for these problems. So if you're thinking about this, I've got a little flash drive on a lanyard here, and you all have done this before with something similar and made a pendulum like this. Now, the faster that I make the omega, and I'm trying to make the omega faster by spinning this faster by moving my fingers around a little bit, I can change the omega. But you notice that the angle changes. Those two are related. They're not independent. And so the faster I make this, I can get the omega going pretty high. The angle gets very close to being an angle that's flush with the horizontal. Or in our problem, the angle gets close to 180 degrees. It opens up to 180 degrees if you look carefully at that problem. So the angle gets close to 180 degrees as my omega gets high, but I can push it to get it very close to 180 degrees, and I can keep that omega going faster and faster and faster. And so I can feel the tension in my hand getting higher and higher and higher, and you can imagine if I spun that fast enough, I might eventually reach a point where the tension was so great that I could snap the rope there if it was a weak string. Sure, why not? Why not? I can feel it. I can imagine that the tension in this lanyard is certainly dependent on omega, on how fast that rotation is going. The tension is going to be smaller down here than it would be up here. Conceptually, you should be able to visualize that. And right there, you can win the problem by knocking out the first two because they don't have omega in them at all. And so those can't be the right answer. You're left with E, and you could pick that just on eliminating units and thinking conceptually about the problem. Now that being said, you can do the problem pretty quick anyways. It's not that hard. So, and get the exact answer, and that's a little more straightforward approach that a lot of people would probably appreciate. You're trying to solve the tension. So I'm going to do an impromptu free body diagram on that pendulum there. You've got the tension acting up at that angle, and you've got the mass of the pendulum, the force being the mass times the acceleration due to gravity. Now I can break the tension up into its components. The tension in the y direction and the tension in the x direction. Something like that. I know that this mass, this pendulum, is accelerating in that direction. It's a centripetal acceleration that is resulting in the pendulum bob keeping a circular path. So I know it's a centripetal acceleration. The velocity is into my whiteboard here. So at this point, the bob of the pendulum is going that way into the board. And I can start working here very quickly. If I can solve the y and x components for t, I can add them as vectors add vectorially, and I can get the magnitude of the tension just like that. So right away I get ty because there's no acceleration in the y. That thing is not moving up or down, it's just the centripetal acceleration. So the tension, the y component of the tension is just equal to mg. Just by looking at that, you know those are opposite and equal. To get the x component of the tension, that is just going to be equal to the mass multiplied by the acceleration. And that's also equal to the centripetal, or sometimes what I've been calling it is the radial acceleration, so a sub r. And that is equal to v squared over r. Don't get those r's confused. This one up here is a subscript, and this one, and you know what, I'll erase that because the r in the problem is actually represented lowercase, so I'll use lowercase. V squared over r. Okay? And that's the instantaneous velocity at that point. Now, the instantaneous velocity is related to the omega, the angular velocity, by this equation. V equals omega times r. And so I just make that substitution. And I simplify it a little bit. Okay, so look at those bottom two. Pretty straightforward. That gives me the x component of the tension, and then I just add those vectorially to get the answer. So I just use Pythagorean theorem, and I get something that looks very close to that answer. If I rearrange it, it looks exactly like that answer. Voila. So you can simplify that, and you see that you get answer E. I don't really have anything to pop on as something to put on a flashcard today. I am going to try and be, personally, I'm trying to be a little bit more rigorous than I have been. I'm going to be dragging out my texts a little bit the next couple weeks, and hitting it a lot harder to be a little bit more accurate and rigorous with some of the things that I'm doing here. I may go back and re-edit some of these videos. For right now, I want to get them out there and have them be accurate, even if they're not quite as rigorous and perfect as they could be. So look for that in the future, and I guess that's it. Hope you enjoyed this problem. Thank you, and I'll see you next time.